and welcome to this case study on a BMW i3 with DC charging. So the fast charging system is not working on this vehicle. That's CCS, so combined charging system. So it does have AC. AC charging was fine, DC charging not working. So let's crack on and have a look at how we tackle this one, which was challenging as ever. So first of all, I'd like to speak about DC charging and just how chargers are different in terms of the information they give back to the owner, driver, technician. This one in particular, this is BP Pulse, so DC charging, so you need a DC charger, of course, but here we have an error message that actually gives us DC charger power module over voltage. So there is a form of a description of a fault code, if you want to call it that. I'm actually not sure what service code 85 is. Nevertheless, there's a little clue in that. And really what I wanted to show you here is the difference between chargers. So on the left, we've got the BP Pulse, as it so happens to be. Gives you a nice breakdown of the various stages of charging. So we've got here charging type selected is CCS, of course. The user authentication, good. Vehicle detected, there's a golden nugget of information. It can actually see that the charger is connected to the vehicle. Communication is okay, another golden nugget of information. Now that comes back to bite me as we go through this case study, which I'll explain as we go on. And then the safety check is okay. So I'm assuming there it's doing some kind of insulation test. Now, by comparison, if you look on the right there, we've got another charger which says communication failed. Totally the opposite of what this charger is saying on the left, because it said communication okay. Some chargers don't give any feedback at all, so it's worth noting that if you can get to often these standalone chargers with a full description of the process of charging, connection, handshake, etc., it will give you a bit of a steer when it comes to your diagnosis. So let's move on. And first one here is fault codes, of course. Using a scan tool, the initial fault code suggests the communication fault between the EVSE and the vehicle, EVSE being the charging station. Now this is in contrast to what we actually saw on the charger. Charger said communication was okay. Here it's saying communication fault with the charging cable, the wall box, or the charging station. So here we are again in the realms of no man's land, conflicting information from the charger and from the onboard diagnosis. But as ever, let's pursue. So where do we go? Communication between the EVSE and the vehicle is over the CP line. So this is the communication control pilot, sorry. And we use PicoScope for this test. So this is, we've actually got a guided test for it. So connect PicoScope to the CP line, connect the charger and look at the pulse width modulated signal. And also something else, some more detail that we'll see as we move on. Now, you'll see here, let's just go on to the next slide because this really looks at it in detail. CP, we are now connected to the mains, we're connected to the grid, so we're measuring the CP control pilot wire behind the charge inlet on the vehicle when we're connected to the charging station. So we are, or should be using a CAT rated probe. Now we would use the differential probe normally. In this scenario and in a number of scenarios coming up, we're in a controlled environment, so on this occasion we're using a ×1 lead. Nevertheless, you must follow precautions, use a CAT-rated differential probe for this test. Either way, what I want to point out here is, first and foremost, is the positive duty cycle on the CP line when we were connected to the EVSE charger is below 7%. Now that is an indication that DC charging is required, a higher level of charging communication. Should be in place on the CP line. Now there's something quite unique happens here. Not only do we have pulse width modulated signal duty cycle, if you look closely, we have what looks to be periodic noise actually superimposed on top of the PWM signal. Now, you may mistake that for noise. It's actually a communication protocol called PLC. Now, PLC cleverly rides on top of the PWM signal of the CP line. And this higher level of communication is required between the vehicle and the charger when DC charging. I've zoomed in a little bit. You'll just see, let me just bring the mouse over. This area on the right here is the zoomed in portion of these, what look to be small packets of data. At this stage, we cannot decode that. We are working on it and we will do. But for now, all we can say from this test is that yes, our PWM signal is below the required 7%, and that digital communication over PLC, power line communication, is ongoing. And that's as much as we can prove at this stage. So where to now? Just a quick look at power line communication. This is really a textbook example, but this is truly what was happening on that previous signal. You see that the green, what looks to be electrical noise, is actually a protocol, a communication that is ongoing between the charger again and the vehicle. In the blue, you'll see the conventional PWM signal, and of course the green there, that is data. So don't be misled by that noise. It is relevant, and the fact that we can capture it means we can prove there's activity, but we can't decode at this stage. So be aware. This brings me on to noise as well on charging systems. So there will be inherent noise on circuits. Now, we have had issues in the past with our own Pico e-Golf that we have here with PLC. It has a similar charging system, and depending on the certain charging stations that you went to, some were more noisy than others, and that was affecting the PLC communication. It turned out to be a software update for the interface between the charge inlet and the onboard charger. Nevertheless, be aware that environmental noise could have a negative impact on PLC. Food for thought. I've just put a link in this slide as well. You'll see that we've done a section on PLC on the forum. I think it may be discussing the Golf case study that we had. So if you can grab that link there and just link across to the forum, that will highlight a little bit more information about PLC. Okay, so a summary where we are right now. Conflicting error messages from DC chargers. Communication is okay and communication fail. So where does that leave you? Dare I say nowhere. We did have a DTC 805519 communication fault with charge cable, wall box or charge station. So I'm leaning more toward communication at this stage because we've got a DTC and an error message from one charger suggesting communication. What we do know is control pilot communication via PWM duty is correct, less than 7%. So the PWM is correct. And PLC communication, power line communication, that signal that rides on CP, is actually present, but we don't know what information is within there. Based on all that information, I decided to change the charging control unit, which BMW refer to as LIM. Oh dear, let's move on. Let me just talk about LIM quickly, the charge interface module, and also a website wiki that really helped with this case study. There are a team of engineers, electronic engineers, R&D guys, automotive wizards, technicians, etc. that all contribute to a website called openinverter.org. And I think looking back on this case study now, I'm not sure how I would have managed without the information within. So let me just show you how pivotal on this diagram the LIM module is. So here is the LIM. This is the interface between charge inlet. See, PP and CP come into the LIM module here. Powertrain CAN also comes in here as well. It also has a hardwired output monitoring the inlet voltage from the charge inlet to the charge contactors. So it's worth noting there. So based on that, you can see just how essential this device is. And my line of thinking was, well, if we have good CP, we have no communication fault code and no communication warning from the charger, this must be the LIM module. No, not the case. Let's move on. And there's nothing worse is when you actually replace a LIM module or replace any module, after all the testing you did, no, it didn't cure it, and it's a heart-sinking moment. So at this stage, whilst it was disappointing, we've got to look at a different angle. A different tactic is what's required here. So first thing I did was change the scan tool, which is clunky thing to do, isn't it? I mean, you should be able to rely on your scan tool. And I also had further attempts at DC charging. So erase all fault codes, go back to a charging station. Again, the BP Pulse one. There are other good chargers out there, remember. What I noticed was DTC has appeared every time we tried to DC charge, but different ones this time. And this starts to change the direction. Let's just have a look at these fault codes closely. Two that stood out for me. So this is with the new LIM module installed. One was 2222842, no charging voltage detected, and 2222877, external module, incorrect high voltage charging status detected. So now there must be some kind of communication, because these are codes that are referring to voltage values and charging status. So my interpretation of that is, for it to come up with those fault codes, it must have had an exchange of data. So let's pursue this. There comes a point, isn't there, where taking away the variables of scan tool interpretation and its terminology used, that measuring live, there is no substitute. You are actually capturing events that are going on as you connect. There's no interpretation. You know which wires you've connected to, you know the signals you're expecting, and you're seeing it in real time. So let me just discuss what's going on in this waveform. We'll have a look at a bigger picture in a second, but I'm connected on channel A to the CP. That is the control pilot. There's a lot of information in the control pilot. I've got the charge inlet DC voltage. Now remember, this is, whilst it is DC voltage, it is not high voltage. What happens is that voltage is converted, stepped down to a safe voltage, and then there is an attenuation factor whereby the voltage that I read between 0 and 5 volts equates to the voltage from the DC charger. So for example, 4 volts may equal 400 volts. Again, this is thanks to the open inverter where I got this information from, and it's proved, having access to this hardwired signal has proved invaluable with this case study. I've also got the DC positive and negative control signals from the LIN to the DC onboard charging units, KLE, BMW. And I've also got a maths channel, which is just monitoring the duty, the positive duty of the CP line. So let's take a closer look at what's going on in here. So let's focus on channel A. You'll notice channel A CP line, that starts at 9 volts. That's the initial connection. So that's how the charger recognizes it's connected to the vehicle. It then also steps down to 6 volts. And for that to occur, the onboard charger and the EVSE must have been happy that the conditions were right at that point in time, because the onboard charger here switches in a different resistor, pulls the voltage down, and is happy at that stage for charging to commence. If we look also, the black math channel at the bottom, that is fixed around about 4.9%. That's reading positive duty. So throughout this initial stage of charging, handshake and final connection, The duty never wavered, it remained at and under the 7% marker. And if we zoomed in, you would have seen PLC communication ongoing. Channel B, this is where the gold is. Channel B is that wire that reads the DC inlet voltage, the voltage coming from the DC charger. Hardwired signal, remember, attenuated in such a way. If we look here on the graph, I think we're at 4.1 volts. 4.1 volt equates to 408 volts. There is a scale that you can use, but you'll notice here that when the CP line, let me bring my marker in again, when the CP line at this stage drops to 6 volts, the EVSE then starts to bring voltage up slowly to 408 volts. So we've now got 408 volts at the charge inlet. But notice on channels C and D, these are the contactors. The contactors are not at this stage closed. These are the contactors that join the DC charger to the onboard charger on the vehicle. So these are within the onboard charger on the vehicle. Notice then how the 408 volts drops back down to 0. So what the EVSE is actually carrying out there is that isolation test. So if you remember, there was a tick on the BP charger, wasn't there, that I think it was a safety check, something like that was the message. That's exactly what's going on here. It's happy with the power cables up to the onboard contactors. They haven't there's no detection of a short circuit there, so we are good to go. That's our safety check complete. Next then we start to slowly ramp up. In fact, let's go to the image on the right hand side. We see how the voltage now is creeping up, and it's the job now of the EVSE to match the voltage of the onboard charger, the onboard battery. So the high voltage battery on the vehicle, which information on PT CAN tells us it was 346 volt. So imagine now we're charging. If we match that, if we bring the charging voltage up to something safe within 346 volts, perhaps slightly higher because we do want a differential, we are going to limit the amount of inrush, aren't we? Where there is a big differential, there'll be a higher current flow. So it's critical that we try and match, as near as damn it, we get charging voltage matching vehicle battery voltage. And what I want to focus on is, here we have closed the contactors. So these are the large contactors on the vehicle that join the charge inlet to the vehicle battery. Prior to that, there's another set of contactors inside the battery, inside the safety box, but nevertheless, we have got contactors inside the onboard charger that close. So we are closing. Now, look here in this zoomed area on the right-hand side. Notice how the voltage at the charge inlet has actually crept up. So it's 4.424 volts, which equates to 442 volts. So how can the voltage at the charge inlet be so high when our vehicle battery is 346 volts? So we've got a huge differential there. The potential for high current flow, damaging current flow, is high. Damage to contactors, especially when they close. So now all of a sudden that starts to fit with the original error message on the BP charger, which was DC charge over voltage. So now it's all sort of starting to make sense. And at this point, you'll notice as the voltage has crept up at the charge inlet, CP communication has halted. So charging will have stopped safety-wise. The onboard charger contactors, they have also opened. You see here on the right-hand side, channels C and D. So they were controlled with PWM. They've now opened. And this is the error. This is that initial error message, no further charging. So the message here really is that the voltage at the charge inlet was creeping up far higher than the onboard battery. Where to next? What I like about this is we've taken away all the variables of the scan tool, of serial data, terminology, and we've actually got raw data to digest. We know physically what's going on in real time. We can make an informed decision. So yeah, how can we have voltage higher at the charge inlet, as I said, compared to what was at the vehicle battery? Let's think this through. For DC voltage to be higher at the charge inlet than the vehicle battery, there must have been an increase in circuit resistance. Just think that through for a second. There had to be. We know that the contactors were closing, or certainly the control of them was present to close them, but we're getting a mismatch somewhere. At this stage, it's time to shut down the vehicle and use the BNC plus resistance lead, because with the vehicle shut down, we can measure the resistance between the charge inlet and the outlet from the onboard charger, because we can physically close or manually close the contactors, because the limb has that job. We can use the wires that go from the limb to the contactors. These are the low voltage 12 volt supply through the coils of the contactors. We can power those up and then actually measure the resistance across those contactors and see if that's where our high resistance is. Now, at this point, we'll do this live. We've actually got the onboard charger off the vehicle. We'll do a simulation of the test that we actually did on the vehicle and see what the values are. And remember, when we're measuring resistance, anything that's carrying high current, we really want to be down in the milliohms range, because any sort of debris on those contacts will be revealed with the milliohm meter, and anything really above, well, 2 milliohm, let's say, across the contactors, we want a good clean contact there, is of cause for concern. So we'll do that now live, and then we'll come back to actually what was wrong with this vehicle. So we have here the onboard charger from the BMW i3, and I've set up a little experiment. We actually did this on the vehicle because these wires here, you can actually get to them. This multi-plug, we can just back pin in there. In fact, either back pin, no, probably be safest to disconnect and use these Pico breakout leads. If you look closely here, hopefully the camera can pick this up. This is the DC EVSE in. So from the charge inlet, the two cables coming into here, then go through a set of contactors inside the charger assembly, and then off and ultimately to the battery through a second set of contactors in the safety box. But that is the circuit. So this is the interrupt, if you like, for the DC charging circuit. Now, using the PicoScope 7, we're going to use the BNC plus resistance lead. We'll connect that to the outlet from the onboard charger and also to the inlet. And what we'll then do is mechanically or manually close the contactors. So using 12 volt supply. In fact, before we do, just have a listen to the difference between these contactors, because this is something I noticed on the vehicle. And by no means is this conclusive diagnosis, but the fact that they're different sort of set alarm bells ringing. So here we go. That was positive contactor on and off. I think the negative contactor is actually a much harsher sudden sound. Here we go again. This is the positive. Negative. Okay, so outside of that, let's just energize the positive contactor inside the charger. And looking at PicoScope there, we can see we have a resistance. So from EVSE in, through the contactors inside here, out and ultimately to the high voltage battery, we have a resistance across the positive contactor of 133 milliohm approximately. What's important here when you're using the resistance lead, make sure you are on the right range. So we're looking for the smallest possible resistance, so that's -5 to 20 ohm. Let's repeat the process. We'll now move across to the negative contactor. So we are moving across to the other cable, moving across to the other input, and now energizing the negative contactor. And PicoScope is still indicating an open circuit. So let's just see if there is anything across there. So we're changing the range now. We are up to 2 kilo ohm, 20 kilo ohm, 200 kilo ohm, 2 mega ohm. It's just open circuit. So there we have it, open circuit negative contactor. Not on the coil side because we can hear it energizing, but on the contact side. What I'd like to do now is minimize PicoScope and let's go to the milliohm and motor tester. So using MTO3A, we'll actually use the Kelvin style measurement, the 4-wire measurement, which accounts for the leads, and see what the resistance is across the good contactor, because remember we can only measure up to 2 ohm with this, but with high micro ohm resolution. We won't bother negative, but we'll see exactly what we get by comparison to PicoScope. So first of all, let's de-energize here, which we are. So it's the 4-wire method, and we are using our Pico breakout leads. We've actually got one bared back so we can get right onto the positive contactor. At this point, there is no point measuring the negative contactor because that is open circuit. Remember, we can only get maximum of 2 ohms measured with MTO3A, but with milliohm accuracy. And we'll make sure we're on the right contact here. So we are EVSE positive coming in through our contactors and then positive out. We will measure temperature, remember, because we do compensate for temperature. I'm not sure what the material of the contactors are. This is set for copper, but if we need to, we can amend that in the software. We'll leave it default, and I'm just going to attach the temperature probe inside the inverter. These have actually been in the workshop for some time, so the entire temperature MTO3A and the probe pretty much stabilized at 23.6. Right, we'll energize the positive contactor. We know this one does work, and we see there, sorry, let me start the software. Right, we are down to 900 and let's say 1,000 milliohm, so 1 ohm. You can also see how that is changing and fluctuating. Now there is no movement anywhere, so this is a change in the resistance. I'm just going to, let me tap the board, see if we get something there. Down to 600 now. So this is the accuracy we've got. What originally we may have thought was a good contactor, in fact at 100, I think it was 170, was it? 180 milliohm recorded with PicoScope and the BNC Plus resistance probe. By comparison to what we've got here, they're both a fail, but this is measuring now to a higher level. So if it was that you had both contactors working, but one of them had a resistance of 500 milliohm, that is a fail. Those contactors need to be replaced. And let's just think about that for a minute. 500 milliohm, that's half an ohm. It's a tiny resistance, but of course the voltage drop that you'll get across that kind of resistance when high current is flowing results in burning. And that's exactly what we've got here. Let's have a look now. So I'm just going to disconnect and show you the damage that was caused. Just lift this out of the vise. And there we have it. So there is the board. And there is the burning and the scorching below the negative contactor. And unfortunately, at this stage, that is a new onboard charger. I'm sure the time will come where we'll be able to get these parts separate, but for now, it's quite an expense. And here we have it. Here are the contactors, or at least the PCB. This is the underside of the contactor. What we found, as you saw, was a high resistance across the negative DC charge contactor. And when we open up the onboard charger, there it is. You can see those burn marks. The contactors had overheated clearly, introducing that high resistance. So yeah, we saw with the BNC Plus resistance lead how we had a value, sometimes an open, sometimes an intermittent. But when we actually drill down to what we thought was the good contactor on the positive side, even that had a excessive milliohm resistance. So in that scenario, it's a no-go. So as ever, verification. So let's get back onto the vehicle with the onboard charger replaced and PicoScope used to verify the repair. We've got some valuable data here for the next vehicle where we have a similar sort of fault. It's often a test that's overlooked because once the vehicle's fixed, we want it out the workshop. Of course, we need paying for that job, and then the next job is waiting to come in. But if you can spend that little bit of time getting the verification, It'll just help going forward. Just a quick indication of what we've got going on here. On channel A is the CP voltage again. We always want that one. That valuable charge inlet on channel B. This time I've sacrificed one DC contactor, so we're just using one here, PWM control. And on channel D, I've actually got the current that's traveling between the EVSE and the vehicle itself. And note the stable voltage and progressive increase in DC charge current. Let's have a look at that in more detail. So same again, just look at CP. Notice how we've got the 9 volt dropping to 6 volts and how it does not switch off. That 6 volt remains, that positive duty is correct throughout this capture. Bear in mind this is 5-second division, so that's 50 seconds across the screen. Here we are again with the EV contactor and system isolation test. Remember, at this point the contactors are still open, it's just testing the line there for insulation fault. The EVSE switches off. It starts to progressively increase the voltage. When the voltage matches that of the battery, and in this case, at this one we are 356 volts to match the vehicle high voltage battery. Let me just confirm that in the ruler legend. So we are 356. So there is a conversion to make there. Nevertheless, what we are not getting is an increase, a dramatic increase above battery voltage, onboard high voltage battery, such that that differential is kept to a minimum. The onboard chargers, contactors are then closed. You see the PWM signal here on channel C, and then look at how progressively that current ramps up. There's no instant rising current, that would denote a short. It's nice and progressive and controlled. That would have kept on creeping up. It's just that we've come to the end of the capture. And there we are at, when we leave this capture, we're already at 63 amps, which is a lot of energy flowing, isn't it, if you think about it. You know, that kind of current, when you think of the damage that a 1 amp current can do when there's a short circuit through a cable, here we have 63 amps and more increasing. So just be aware of that. What I like about using the current clamp, it's completely non-intrusive. We just wrap that around the cable. You know, no gloves required at that time. We are not intruding into the insulation in any way, and we gain this valuable data. Okay, so let's conclude here, and forgive me, this is a wordy slide, but I'm going to go through it word for word because the value in it is essential. Not all EVSE's main chargers are made equal. Choose a charger that provides valuable feedback. You saw the difference in the first slide there between the BP Pulse charger, or the good chargers are available, and the other charger that gave us nothing really. In fact, really a bit of a bum steer, wasn't it? Said communication had failed, try again. A word about PLC, I mentioned it before. There is always this concern that I have about noisy environments, and what looks like noise on the CP line is actually communication, PLC, high-level communication data between the onboard charger and the charging station, EVSE. Any noise in that environment that intrudes on CP has the potential to influence and knock out PLC. So I have found, this is my own experience and there's no real logic behind it, that sometimes a standalone charger, the one I used here was at the race course, there's another one local to us at a restaurant, car park of a restaurant. And often they seem to be a little bit more insulated from noise. I seem to get a connection straight away, especially with our e-Golf that relies on PLC. Whereas when I've attended a charging lane where there are multiple chargers, it's been a case of connecting, disconnect, connect, disconnecting. Eventually that handshake and PLC is complete and we're off. So just be aware. Of course, we know this already, not all scan tools are made equal. The dealer tool is the best tool. Generic tools, they're great tools out there. We use one ourselves. Where I struggle is sometimes their terminology and interpretation of codes and vehicle components. It can leave you a little bit adrift. So as ever, take it with a pinch of salt. An in-depth understanding of the charging system operation And I've put here beyond the vehicle manufacturer literature is often required. Look for industry standard papers, because we know that charging systems are governed and ruled by industry standards, and those standards are out there, and there's some great documentation that explains exactly how CP, PP work, how AC charging works, DC charging, and the standards within. So once you've got that under your belt, the vehicle manufacturers can't deviate from that at all. They've got to stick within. Finally, apply PicoScope to measure live where it's safe to do so. Thanks to the information that we had from Open Inverter, we were able to understand just how this truly worked. This attenuated voltage wire that gave us the charge inlet voltage, that was invaluable. Again, I've mentioned it, it removes all the variables, doesn't it? You're measuring live in real time on signals that you are connected to. You know what to expect on those cables. You get the sequence of events, don't you? We were able to capture exactly what the charger was doing, where it was doing its safety test, its installation test, where the voltage was ramping up. Then we could clearly see how the voltage was creeping above the threshold. It was higher than battery voltage. We were able to see that the CP immediately interrupted the communication line, the charging contactors open. So we knew to a certain degree all that was in place. Let's just quickly go through those points. Point 1, charge connection and handshake. The CP voltage at 9 volt and the PWM duty at less than 7%. That was in place. Remember, that's positive duty. The onboard charger, how it accepted, or charger acceptance of the EVSE at the charging station. The onboard charger was comfortable. It recognised it was connected. It lowered the voltage to 6 volt and permitted charging. We saw the EV insulation test, of course. Operation of the DC charge contactors on channel C and D. If you remember, we could actually see those operate. And we also saw that voltage creep up, the incorrect charge inlet voltage compared to HV battery voltage. And there is somebody, well, a number of people I must thank here, and that is Hevra, the Hybrid and Electric Vehicle Repair Alliance. Great team there, just often the shoulder to cry on sometimes, but just to bounce ideas off. And also Open Inverter, the team there, the guys, anybody who's posted there, thank you so much. Right down to the level of CAN communication and creating a DBC file for the CAN network. It is awesome work, so thank you so much. I hope you enjoyed the case study. Any questions, please leave them here underneath in the comments. And yeah, I'm going to post these waveforms on the waveform library, so you'll see good and bad, and I'll try and link back to this video. So thank you very much for watching.